Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Previously we discussed how a tangent frame can be calculated for any triangle mesh, given that it contains vertex normals and vertex UVs. We didn't, however, look at how a normal map is constructed, which is obviously less relevant for using it, but is important to know nevertheless. In general, the application that creates a normal map uses the low-res version of the model to calculate a tangent frame like we did, and then transforms the object space normals of the high-res model to this tangent space. It then writes the resulting vectors to the normal map. A normal map is therefore an encoding of the high-res model's normal vectors. In order to decode the normal map, we can transform it back to object space by multiplying it by the inverse of the TBN matrix that was used for encoding it. Note that the TBN matrix is an orthonormal matrix and therefore it can be inverted simply by transposing it. From this decoding transformation, we get our modified interpolated normal vectors, which we can use for lighting. Now it should be obvious that the calculated normals could deviate from the original if we don't use the exact same TBN matrix for both encoding and decoding. Also, the algorithm for applying the transformations should be the same. What I mean by this is, well, the TBN calculation itself, of course, but also when the TBN vectors are normalized, how mirrored UVs are handled, and so on. When we calculate the tangent vectors, we don't actually know if the normal map that we are going to transform with it was actually computed using the same algorithm. If only there was a standardized way of doing this, which everyone would use, so we didn't have to worry about these details. And luckily there is one method that was proposed by Morten S. Mikkelsen, who wrote a thesis on the subject and also implemented the algorithm that is known as MikkTSpace. It's been adopted by most content creation tools and therefore it's also common for game engines to use it for calculating tangent frames. It produces the same TBN matrix for both the encoders and decoders using the same algorithm, and as we'll see in a minute, it also explains how to use the resulting tangent space. The code for MikkTSpace can be downloaded from a public GitHub repository and consists of only a header file and a C file. Here we also find a link to a page with a brief explanation of what it is and how to use it. I'll clone the repository first, where I just copy these two files into our own solution. Well, actually let me copy the whole folder so I don't have to create it myself. Obviously we don't need the git folder and the readme file, so we are left with the files that contain all the code. Let me actually create a folder that will contain the license files of any third-party software that we use. MikkTSpace has an MIT license, which means that we can use it without any constraints as long as we include the license text that contains the original author's name, so that's what I'll do next. So far we have been using DirectX text library, which is also MIT, and I might include a file for that later as well. For now I just copy and paste the license text from the source code. In order to use MikkTSpace for tangent vector calculation, we need to call this function and provide it with an interface and a pointer to the mesh data. I'll explain this in a minute. First, let's include the header file and add a new function that will call into MikkTSpace. As I mentioned, it has an interface with a few function pointers that need to be set. This is similar to how we use the renderer interface to point to low-level renderers functions. I'll list all function pointers here first and then write the functions that they'll point to. Let's suppose we have set all these function pointers, then we can point to this interface in an instance of MikkTSpace context. It will also contain a pointer to our own mesh data. Finally, we call this function which will generate the tangent space. That's all we have to do in order to use this code. What's left is to write the functions that are used for feeding data into the tangent generation algorithm. I'll do a bit of copy-pasting in order to save us some time here. Here I'm changing parameter and function names a bit in order to conform to our coding conventions. So we need to provide a function that returns the number of polygons in the mesh. In our case, we only use triangle meshes, and therefore we return the number of triangles in the mesh, which can be calculated simply by dividing the number of indices by 3. For the same reason, the number of vertices for each face is always 3. For the vertex position, we get a face index and a vertex index for that face. Again, since we only have triangles, we can compute the index in the array of vertices and return its position. And we can provide the normal vector and vertex UV coordinates in a similar fashion. The tangent vector and its sign are returned to us in the last callback function. In this case, we can read the data from the parameters and put them in the vertex tangent vector. Note that we put the sign in the W component of the vector. Finally, we can assign each function pointer to point to the corresponding function. Now we can call this function to calculate tangents using MikkTSpace. When building the project, we get a few warnings which I am going to address next. In this function, we are not using any of the parameters since the returned value doesn't depend on them. I'm going to mark them with maybe unused attribute. The remaining warnings come from the code in MikkTSpace, which we are obviously not going to change. The warnings are mostly because of scoped local variable redefinitions, which the compiler warns us about. For example, here the I variable is already defined in the scope outside of the for loop, where it is defined again. This is not wrong, but it's confusing and error-prone for maintainers. Since we are not maintainers, we can simply turn off these warnings, but only for this file. This can be done by right-clicking the file and adding extra command line compiler options that disable warnings with the specified number. Opening the CPP project file, we can see that this line is added where the C file for MikkTSpace is included for compilation. It is, however, only added for debug build, so I have to do the same for release build, since I guess I forgot to select all configurations when I set the additional options. And there we have another line for the release build. Now we can re-import our model and calculate its tangent vectors using MikkTSpace. Opening it in the editor will save it for testing, so I'm gonna head over to that location and rename the model file. And as we can see, it looks the same as before. We can also undo the sign reversal from the last video and see if that introduces the same artifacts. It appears that we also have to reverse the tangent sign when using MikkTSpace. As I mentioned in the last video, this is caused by our FBX importer when importing the UVs, and I'll fix it in the next episode. Okay, this looks fine now, and other than the fix that I just talked about, we are done with the implementation of normal mapping in Primal Engine. One case that we still need to cover though is when the user for some reason wants to import tangents directly from the FBX file instead of calculating them. In that case, we already have the code that extracts that information. However, we need to examine tangent vectors that belong to the same vertex position and split the vertex if those vectors are different or have an opposing handedness. So if the tangents array is not empty, We'll call a new function that will process tangents in about the same way we process extracted normal vectors. Here we need as many tangent vectors as there are positions. In other words, we need the unindexed tangent vectors. Since this function is rather similar to other process functions, I can copy and paste most of it from the others. So this first part is actually exactly the same. And the second part is where we copy the vertices and split them if necessary. We get a reference to one of the tangents first. And we'll use it as the vertex tangent. If all other tangents for this shared vertex are the same, then nothing changes. However, if there is a tangent vector that's different, we have to split this vertex. We can use DirectX math to compare tangents of vertices that are shared between triangles and see if they differ more than a small amount, which is defined as epsilon. I'm going to remove this using namespace so that we have to specify in which namespace the functions and variables are defined. You don't have to do this, but I find it easier to understand the code if I can see that, for example, the value of epsilon is the one coming from the math namespace and isn't a constant that we defined somewhere in this file. Now we can compare two tangent vectors like so. And the rest of the code remains the same. Before wrapping up, we need to do one more thing if we are going to use MikkTSpace as the default for calculating tangent vectors. Here the document states that we don't need to normalize the interpolated normal and tangent vectors in the pixel shader where we apply the normal map. So we can go ahead and remove the calls to normalize function, which saves us some work that's done per pixel. We can read the same explanation in the source code as well. And this concludes the episode about normal mapping. I hope my explanation helped you to better understand the role that tangent spaces play in applying normal maps, if you didn't already, and that you enjoyed watching this video. In the next episode, we are going to introduce physically based rendering. In preparation, I'd like to recommend watching this video that explains the concept and mathematics of PBR very well. You can find the link to the video along with some other resources in the description below. And as always, thank you so much for joining me, and I'll see you next time.